All right, so let's get started. In the last lecture that we had, we talked about the center of mass. We started talking about the center of mass. The definition of the center of mass is that it's that one point associated with a system of particles or a solid object, for which has these two fantastic properties. One of them is that you can pretend that the entire mass of the system is concentrated at that one point. And the second is you can also pretend that all the forces, all the external forces acting on that object are all acting at that single point. And so that is something that this is a concept that you have been using right since the beginning of the course when you started drawing force diagrams. So for example, I think we mentioned this in class. For example, we talked about we talked about whenever you have drawn force diagrams, they kind of look like this. Suppose you've got a ramp and you have an object sitting on the ramp. Then if you were asked to draw the forces on that object, you would draw them like this. Weight of the object acting down like this, maybe a normal force like that, an external force, the force of friction if the object is moving up the ramp. So this is how you've always drawn force diagrams. And notice that in drawing this diagram, you're really pretending that the object is a single point mass which is located somewhere near the center of the object, and all the forces are directly acting on that single point mass. However, in reality, we know that that's not true. The gravitational force, for example, acts on every atom and molecule inside the object. The friction force obviously just acts at the surface, so the bottom surface of the object. The normal force also acts at the bottom surface of the object, and so the forces don't act in reality act at that one point, but the center of mass has this wonderful property that we can pretend that all the forces act at that one point. So the center of mass is that one point associated with an object, which allows you to pretend that the object is a point mass. So the entire object can be treated as a point mass. And the second wonderful thing that the center of mass does for you is that you can pretend that all forces act at that one point. Right. Okay. So how do you find a wonderful point like this, which has these nice properties? So we talked about the formula for locating the center of mass, and so that formula was right here. So these formulas tell you how to find the center of mass of a system of point masses. These point masses have masses m1, m2, m3, and so on, and they're located at positions x1, y1, z1, x2, y2, z2, x3, y3, z3, and so on, right? So if you have a bunch of point masses, you know what their masses are, and you know their positions, then you can use these three formulas to find the x, these three formulas, I mean, to find the x, y, and z coordinates of the center of mass, right? And in class, I think I derived the fact that from these three formulas can be written in a very compact way using vector notation like this. So the position of the center of mass, position vector for the center of mass, is equal to mi ri divided by capital M, where capital M is just the total mass of the system of particles. So capital M is equal to summation mi, right? I think I showed you how this formula comes about, but in case you have forgotten, since it's been a while, I'll just quickly go over it one more time. So the formula for the center of mass was summation. So x coordinate of the center of mass was given by summation mi xi divided by capital M, where capital M obviously is the total mass of all the particles. YCM is equal to summation mi yi divided by capital M, and ZCM is equal to summation mi zi divided by capital M, right? So to see, so I told you that all three of these formulas can be summarized by this equation. Position of the center of mass, position vector of the center of mass is equal to summation mi ri divided by capital M. And to see how this comes about, it's very simple. All you have to do is just multiply the first equation by I hat, second equation by j hat, and third equation by k hat, right? And then all you have to do is just add up the left sides, add up the right sides, and so you get I hat xcm plus j hat ycm plus k hat zcm on the left side, which obviously is just nothing but the position vector of the center of mass, rcm. And what do you get on the right side? On the right side, notice that you can factor out the summation mi and the capital M. So you're left with summation mi over capital M, I hat xi plus j hat yi plus k hat zi. So that is just equal to summation mi. This quantity is just the position of the ith particle, position vector for the ith particle. So we're going to call that ri divided by capital M. And so we have derived the formula for the position of the center of mass. Okay, so what can we do next? The next thing that we can derive is we can derive a formula for the velocity of the center of mass. Okay, so moving on to the next slide. All right, so why would the center of mass have a velocity? So if all the particles are at rest, then their center of mass will be at rest, obviously. But if the particles are moving around, then the center of mass would not necessarily be at rest, right? So if you guys were in class, I would have used this analogy that you're all sitting in your seats right now. And so if I calculate the center of mass, if I treat all of you as point masses, and I know your x, y, and z positions, suppose, then I can calculate a center of mass of all the students in the class, right? But when the class ends and all of you get out of your seats and start walking, then your positions are all changing, right? So if I calculate the position of the center of mass at any point of time, the next instant it will be a different position because all of you have moved, right? So the center of mass could be changing position and it might have a velocity. So there might be a velocity associated with the movement of the center of mass. So that's what we're going to calculate next. And so let's see how we would get that. All you have to do is just take a derivative. So to get the velocity of the center of mass, just differentiate the equation that we just got. So just do a ddt, derivative with respect to time. And so that would be, so ddt of rcm would be equal to, notice that mi's are all constant, the masses are all constant, capital M is constant. So the derivative just really applies to the ri, it just acts on the ri. So you get summation mi dri dt divided by m, right? Now you remember from chapter 3 that if you take the derivative of a position vector, you get a velocity vector. So the velocity of the center of mass is equal to summation mi. What is dri dt? That is just, ri is the position of the ith particle. So dri dt is just the velocity of the ith particle, mi vi divided by m. And if you want, you can multiply both sides by capital M to get this equation. MVCM is equal to summation MIVI. All right. Now, what is this MIVI? It's the momentum. MIVI is the momentum of the ith particle, right? Remember, momentum is mass multiplied by velocity. Let me just write that. P is mv. Remember that from the beginning of the chapter. So this is just some vector sum of the momenta of all the particles. So we can write that as, let's call that capital P, the total momentum of all the particles, right? Okay, so I'll just total momentum of all the particles. And total, by the way, is in the sense of vector addition. So if you vector add the momenta of all the particles, you get capital P, right? So what does this equation tell us? So the equation that we just derived is mvcm is equal to the total momentum of all the particles in the system. So you can see that as far as the total momentum is concerned, you can just, if you just consider a hypothetical particle of mass capital M moving with velocity vcm, that would have the same total momentum as the entire system, right? So a single particle of mass m moving with velocity vcm can represent the whole system, right? And that is what we talked about in the beginning of this lecture, that the center of mass is that one point where, if you assume that there is a single mass capital M located over there, then it represents the entire system. And that's what this equation is telling us, right? Okay. Now, there's one more thing that you can do here. You can take one more derivative of this equation, right? So let's go ahead and differentiate this one more time. Differentiate again. Then we get capital M dVcm dt is equal to dP dt. Now, this dP dt is something we had learned earlier on in this chapter. We had seen that dP dt is just equal to d capital P dt is just equal to F external. So we had proved that if you have a system of particles, F external, the derivative of the total momentum of the system is equal to F external. And in fact, this is the equation from which we derive conservation of momentum. So if F external is equal to 0, then dP dt is equal to 0 and P is equal to constant, or total momentum of the system is constant. So this is an equation that we are familiar with. So let's just plug that in as well. So this is equal to F external. We had seen this earlier. So from here we can conclude that M A center of mass is equal to F external. This is a very important equation. Okay, and I should just put a summation here. Okay. So this is a very important equation because what it's telling us is that the motion of the center of mass of a system of particles is determined solely by the external forces acting on the system. So let me write that down. Motion of the center of mass of a system of particles is determined solely by the external forces acting, I mean, on the system. Another thing that you can see from this last equation is that it looks very much like the equation of a single particle. Force equals mass times acceleration, right? So this is again telling us the same thing, that you can represent the entire system of particles, like it might have a billion particles in it, but you can represent the whole thing by just one particle of mass capital M, which has an acceleration equal to the acceleration of the center of mass, right? So once again, you can see that the center of mass represents the whole system. You can, all right. Okay. All right. So now let's look at a couple of. Okay. Let's just see what the next slide is. Yeah. So let me just. So now we are on slide 28. Let me just explain this slide, and then we will look at a few applications of these ideas. So we've so far talked about system where you've got a set of discrete masses, point masses, and we know how to find their center of mass, right? Let's say the center of mass is somewhere over here. Okay. Now, what about if you have a continuous mass distribution, like a solid object? It's not a system of point masses. How do you find the center of mass of this? Well, in that case, you use the same procedure, right? It's the same kind of thinking, but you have to bring in calculus, right? And the equations for that are given on the slide. We are not going to get into how to derive these equations or how to use these equations, but the reason that I'm showing this to you is just to sort of have some continuity. We were talking about point masses. I'm telling you that you can apply the same ideas to find the center of mass of a solid object, right? We are not going to get into the details of how exactly to do it. The only thing that I'm going to mention is that if the solid object that we are considering is uniform, has a uniform mass distribution, and if it also has a natural point of symmetry, like for example, if you have a thin rod, then its point of symmetry is the center of the rod, right? If you have a sphere, then obviously the point of symmetry is the center of the sphere. If you have a disk, the point of symmetry is the center of the disk. So if you have a symmetric object with a uniform mass distribution, then it's not difficult at all to guess where the center of mass is going to lie, right? Okay, what if you have a rod which is not symmetric? So let me just draw that over here. So what if you have a rod? So if you have a symmetric rod, I mean a rod with uniform mass distribution, the center of mass will just lie at the center of the rod. But suppose you have a situation like this where let's say this side of the rod is made of wood and this side of the rod is made of iron. So this side is obviously a lot heavier. The right side is obviously a lot heavier. Where will the center of mass of this system lie? The answer is it would not be at the center because the mass is not uniformly distributed. It would be somewhere maybe over here on the side of the iron or the heavier part of the rod. Whereas for a symmetric, this is a symmetric, uniform mass distribution. Uniform mass distribution. And this is non-uniform mass distribution. And the center of mass here lies at the geometrical center. All right, so the only point that we made here is that if you have a uniform mass distribution, the center of mass will lie at wherever the geometrical center of that object is located. And if you have a non-uniform mass distribution, then the center of mass will not lie at that geometrical center. It will be shifted more closer to the heavier part of the object, right? Wherever you have more mass. Okay, so that should be pretty intuitive. Now, you can also, the center of mass of an object can very well lie at a place where there is no mass. So for example, suppose you have this donut which is empty. The middle part of that is empty. So that would be a really boring donut. Suppose you have a donut like this where the middle part is empty, and let's say that this portion, the part, I mean the donut part, is uniform. The mass distribution is uniform. So where would the center of mass lie? It would lie at the point of symmetry, which is the center of this object, even though there is no mass located over here. Okay. All right. So now let's look at a couple of applications of these ideas. This problem is fully worked out on the slide, so you can just try this on your own. Let's look at this problem. So you've got three particles. You have the masses of the particles. They're all the same. You have the velocities of the particles. Actually, you've got the velocities of two of the particles, and you're told that the center of mass of the particle of the system is at rest. All right. So like we've always done in class, so what I would have told you at this point, if this were a lecture in class, is that take a moment to think about this problem and see if you can set it up. That's what you should do right now. Pause the video if necessary and see if you can apply any of the ideas that we just discussed to figure out this problem, right? Okay, I'm going to now work this problem out, but I would recommend that you first, whenever I do this, like I would always recommend that you pause the video, think about the solution, and try to work it out yourself before seeing how I do it. All right. Okay. All right. So what do we have? So this is the problem on slide 31. Okay. So what we are given is the masses of all the particles. So all of the particles have the same mass. So M1, M2, and M3 are all the same. They're all equal to 1 kg. What else are we given? We have the velocities of two of the particles. So V1 is equal to 3i hat minus 2j hat. V2 is equal to 3i hat minus 6k hat. V3 is not known. And we are told that the velocity of the center of mass is equal to 0. So the center of mass is at rest. Okay. So we want to find out this missing velocity. So how could we do this? Obviously, what we could do is we could just apply this equation. Capital M VCM is equal to summation Mi Vi, right? So what is capital M? Capital M is the sum of all the masses, right? So capital M is just sum of all the masses. So that's just going to be M plus M plus M, which is 3M. But that doesn't matter because the left side is going to be 0 anyway. So it's 3M multiplied by 0 is equal to summation Mi Vi, right? So let's just plug that in and just solve for V3. That's all that you have to do. So 0 is equal to M multiplied by V1. So 1 multiplied by 3i hat minus 2j hat plus 1 multiplied by 3i hat minus 6k hat plus V3, right? And now we just have to solve for the vector V3. So it's just going to be 0 is equal to 3i. So 3i plus 3i is 6i minus 2j minus 6k is what we have here, plus V3. And so V3 is just going to be minus 6i hat plus 2j hat plus 6k hat. And that's the answer. Right? So all that we did was just apply the formula that capital M times the velocity of the center of mass is equal to the total momentum of the system. Okay, now moving on to, oops, what happened here? Okay, let's look at this problem. And once again, read this problem and see if you can set it up yourself. And then we are going to discuss this problem. Okay. So we are discussing the problem on slide 32. Before we talk about this problem, it's probably a good idea to just look at slide 33, because slide 33 we've already talked about before. I mean, the ideas we've already discussed here. It's probably a good idea to just look at this first, and then we will attack the problem. Okay, so this equation at the beginning of this slide, we had just derived a little while ago, right? So let's once again consider what this equation is telling us. So remember that I derived this equation right here. Summation of all the external forces, sum of all the external forces is equal to mass times the acceleration of the center of mass, right? So sum of all the external forces is equal to the total mass of the system multiplied by the acceleration of the center of mass. All right, so this equation is really telling us that the motion of the center of mass is only affected by the external forces acting on the system. It is not affected by any internal force. And what's an external force and what's an internal force? We've talked about this many times. External forces are forces that are coming from outside of the system. Internal forces are forces exerted by one part of the system on another part of the system, right? So the motion of the center of mass is only affected by the external forces on the system, not the internal forces, right? So one example of this is shown in this diagram over here. Suppose you have an object, a shell, that's launched from a certain point, and then at some point after being launched, the shell breaks up into two pieces, right? The two pieces will go their own separate ways, but the center of mass of the two pieces will continue as if nothing happened. Why is that? Because the motion of the center of mass is only affected by external forces. The forces of the explosion are all internal forces, because of the two pieces pushing on each other. They are not, they don't affect the motion of the center of mass. So the center of mass of the bomb will just continue as if nothing happened. And you can see that it will just continue the parabolic trajectory that the shell would have followed had it not exploded, right? So that's a very important and useful idea, and you often use it in doing problems, right? So I'm going to show you the next two slides, which are slide 32 and 34, are both applications of this idea. I'm going to work through slide 32 as an example, and I will let you try slide 34 yourself. It's very, very similar to, the idea is very similar to what we're going to do in slide 32. But once again, to repeat myself, what the main idea that we are going to use here in doing the next problem is that the center of mass of a system of particles is only affected by external forces. So if internal forces changes a system in some way, like if a solid object breaks up into a couple of different pieces, then the pieces might be doing their own thing, like traveling in different directions and stuff like that. But the center of mass of the system, center of mass of all of those pieces, will just proceed as if nothing happened. All right? Okay. So let's look at the problem on slide 32. So this problem says that a bomb is launched vertically from the ground with a velocity of 30 meters per second. When it reaches the highest point of its trajectory, it explodes into two fragments which travel horizontally at 10 meters per second in opposite directions. What is the height of the center of mass of the fragments 1 second after the explosion? Right? Okay, so here is our, so this is the problem on slide 32. So the bomb is launched vertically from the ground with a velocity of 30 meters per second. Okay. And then it reaches a point over here, and which is the highest point of its trajectory. And there it breaks up into two pieces. And I'm just going to draw the two pieces in different colors, a different color. So here is one piece which goes off like that. And here's another piece which goes off like that in opposite directions. And you have to find what is the height of the center of mass of the two pieces 1 second after the explosion, right? So the two pieces will do their own thing. So they'll follow parabolic trajectories. Like this one will go that way, this one will go like this. And so you might at first think that this is a complicated problem. You have to figure out where each piece is going to be 1 second later, and then use the center of mass formula to find where the center of mass of the two pieces will be. And that's certainly a reasonable way of doing the problem. But a lot easier way of doing the problem is to just remember the fact that the center of mass will not be affected by the explosion at all, because the explosion is all internal forces. The motion of the center of mass is only affected by external forces, and the only external force here is the force of gravity, right? So the center of mass will proceed as if the explosion never happened, right? So where would the object have been if it had not exploded? So it would have just started from the top with zero velocity, and then it would have descended by a certain amount. I'll just use a different color for the center of mass. So the center of mass would probably be somewhere over here, exactly where the object would have been if it had not exploded, right? After 1 second. So that's all we need to find. So it just becomes a very easy kinematics problem. How much will the object descend, or where will the object be 1 second after the explosion? So to do that, I mean, it's entirely up to you how you want to calculate this. There's many ways of doing it. It's just a simple kinematics problem. Where is an object is launched with a certain velocity, where is it going to be 1 second after it reaches the highest point of its trajectory? There's multiple ways you can do it. We'll just do it like this. Let's just find out how high the object rises, right? So to find that, we could just use the third kinematic equation. So we'll first find the height at which the explosion happens. To do that, we'll just use the first kinematic equation, which is, sorry, the third kinematic equation, which is V final square is equal to V initial square minus 2G 2G Y final minus Y initial. We'll just take Y initial to be 0. Okay, so we are solving for Y, right? So V final is 0 because the explosion happens at the maximum height. V initial is 30 square minus 2 times 9.8 times Y. So you can solve for Y from here. 30 square divided by 2 times 9.8. Let me just plug that into a calculator. Okay, so that comes to 86.93 meters, right? All right, now, so that's the height it is. So it's at that height of 86.93 meters at the top with 0 velocity. And how much does it descend in 1 second, right? So location of center of mass after 1 second would be, again, we could use the second kinematic equation for that. So Y final is equal to Y initial plus V0t minus half gt square, right? The initial velocity is 0 because it's at the top, right? And Y final is what we are looking for. Y initial is 86.93 minus half times 9.8 times 1 square, right? And if you plug that into a calculator, half 9 times 8, 1 square, if you plug that into a calculator, oh, I'm so sorry. I think I had the first one wrong. That was, so 30 square divided by 9 times, divided by 2 times 9.8. Let me just work that out again. 91.83. So let me just fix that. I'm sorry about that. This should be 91.83. You see, I'm so used to you guys correcting my mistakes that it's difficult to do it all by myself. Anyway, 91.83. All right, so if you plug this in, and then if you do, let me just do the rest, minus half 9.8 times 1 square, that gives me 86.93. So 86.93 was the final answer. So that is where the center of mass of the object would be 1 second after the explosion, and it's the same point where the object would have been if it had not exploded. Same place where the object would be if it hadn't exploded. All right. So the main idea that we used in this problem is that the center of mass, the motion of the center of mass, is strictly determined by the external forces. Internal forces, such as an explosion, might cause different parts of the object to just go off and do different things, like fly off in different directions, but that does not affect the motion of the center of mass. So I have another problem in the PowerPoint, which is you can solve it easily using the same idea, and that's this one. It's very similar to the problem that we just did. I would recommend that, and I've also put some hints on the slide. So I would recommend that you try this problem on your own. I think there's a similar problem in your mastering physics as well. All right, so that concludes chapter 8, and that's really all that we have for the next exam. I'll see you in the next video. All right.